Okay, we have one more video, one last idea we've got to talk about. Something called a Van Hoff factor. Oh, and depending how I edited the last video, my last video definitely ended suddenly when I originally recorded it because I said I was going to do Van Hoff factor in that video, and I accidentally pressed the stop recording button. So I may have edited that out, but if not, this is indeed the right place to be. So what is a Van Hoff factor? We're going to use this with a symbol called I. And for many substances, I is going to be 1. What this represents is how many molecules... Let's see how to word this. So it's going to be how many particles come from one molecule dissolving in a solvent. So what the heck does that mean, and why would this ever be different? So for example, I have a sugar, C6H12O6. I add it to some water. It stays C6H12O6. I equals 1. But, like we learned in 1211, let's say instead we add some NaCl. Does it stay NaCl when we put it in water? Well, no. We know that, right? It turns into Na plus and Cl minus. So each one NaCl becomes 2 separate particles, an Na plus and a Cl minus. So we say here, I equals 2. And so if we have more molecules, like let's say we had FeCl3, we put that in water, we get 1 iron and 3 chlorines. That's going to be I equals 4. Now, what if I add KNO3? What do you think I is there? I want you to try it. Did you get I as 2? If you got I as 5, the problem is NO3 is a polyatomic ion. We know polyatomics stay together as a single unit. So KNO3, potassium nitrate, becomes K plus and NO3 minus. So it's 2 separate particles, so I equals 2. The reason this is relevant is we said colligative properties are based on how many molecules are dissolved, not their identity. Well here, these molecules, when we dissolve them, are going to actually make multiple different things that are going to interact with our solution. So when you dissolve a mole of NaCl, it's really 2 moles of particles. So there are 2 moles that are going to be related to our colligative properties. Now, this is what we're going to do for most calculations. Technically, the Van Hoff factor isn't always exactly as predicted. It has to do with how things dissolve and how they interact with each other, that you can actually get I's that aren't exact whole numbers. Like you can find, I think for NaCl, I think the I is 1.9. It might be something a bit different. And as a fact, it doesn't really function quite like 2 particles. It functions more like almost 2 particles. Having said that, unless a problem tells you to look this up in a table or gives you an I that's not like a whole number, you should assume, because it works well as a good estimate, it's a good starting point, that it's going to be however many particles this would break apart if it's an ionic compound. Or I is 1 if it's something that wouldn't break apart. So how does this affect our equations? So we can add it to all 3 of these. So we had freezing point depression. We just put an I in front, times molality times Kf. Same for boiling point. It's I times molality times Kb. And then finally, osmotic pressure equals I times molarity times R times T, times temperature. So all it does is it adds this factor out in front. One thing about doing problems using Van Hoff factors is they're much easier when the problem says, look up your Van Hoff factor or notice it. And then you go, oh yeah, I've got to pay attention to I. Oh, I's 2 or I's 3. What happens to a lot of people, though, is in later problems, when they just get told, you dissolve some NaCl in some water, what's the freezing point? They don't think to themselves, oh wait, I. That's ionic. That breaks apart in water. That becomes Na plus and Cl minus. I is 2. They go, it's a freezing point problem, M times Kf. And then they get that problem wrong by a factor of 2. I find it's helpful, and I know I wanted to introduce the first way of doing it, how we did it in the previous video before this, because I wanted to get an idea of how these different systems work before we worried about, oh wait, what if things break apart? But if you just always put I there, and if it doesn't break apart, say I equals 1, it will help you get these problems correct much more often. So let's take a look at an example of where it's relevant. So we're going to, I'll make a slide for this. We're going to calculate the freezing point of an aqueous, remember aqueous is water, 0.0800 molal iron 3 chloride. That should be an E. I'm just going to rewrite it. FeCl3. Calculate the freezing point of an aqueous 0.800 molar FeCl3 solution. And from earlier, our freezing point temperature, as we know for water, is going to be 0.0 degrees Celsius. And our Kf is going to be 1.86 degrees Celsius per mole. Or some will say negative 1.86. Either way is fine as long as you're consistent with how you figure out your answer in the end. So now it is I molality times Kf. Here I is 4, since FeCl3 turns into 1 Fe, 3 plus, and 3 Cl minuses. So I is 4. Then your molality, we're told, is 0.0800 molar. If you've been given moles and kilograms, you could have calculated it yourself. If you were given grams, you'd have to do a molar mass conversion. Basically, it's a problem that this is the fastest way, and other steps can be added to make sure that you're good at doing those. Also, because in practical cases, there'll be many times in lab where you might need to figure out all the way from, okay, I've got this substance, how much do I put in? I know how many grams to make this solution. So at some point, you're probably going to have to calculate this molality. So we have you practice a lot in problems. But for now, we just have this, and then our Kf is 1.86 degrees Celsius per mole. So we plug all of those in, and we'll get 0.595 degrees Celsius. So our freezing point is going to be 0.00, actually. It's got 2 zeros in the freezing point about measurement accuracy. That was really bad. 0.00 degrees Celsius. Minus 0.595 degrees Celsius. We get that, we get 0.60 degrees Celsius negative. It was depressed, negative 0.60 degrees Celsius. So that's how you do this with a Van Hoff factor. It works the same way with any other type of problem. You just, like osmotic pressure, you would just use that I. So if you found an osmotic pressure without it, I is 4, multiply your answer times 4. Just make sure not to forget this I term, because it's how many particles are actually in your solution, because some of your types of compounds we're using are going to dissolve and break apart into multiple pieces. Some dissolve and they stay together, like sugars, for example. Any of our covalent compounds that we worked with. That's why in 1211 we made this emphasis on, oh, here are ionic compounds, here are covalent. The ionic break apart, here's how they break apart. Learn your polyatomics, all those types of things. Covalent, they don't break apart. Well, it's not the only reason we taught it, but it's what way it comes up now. So that's a good place to stop this chapter at. I do think these, I will point out, these are problems. Not just the Van Hoff factor, but in general, this whole chapter with all these, there's like 3 or 4 different concentration calculations. There's 4 colligative property calculations. Practice these because you want these things to be quick, because what's nice is for a lot of the problems, not that protein problem, that's going to take some thinking, but most of them, it is very systematic. And that's part of our goal, right? We want you as a chemist to be like, when I see a molality, I know how to calculate that. When I want to know an osmotic pressure, I can calculate that. And then when you need to use it for something, you'll have to put your mind to it more, and you might have to do some more manipulation. But these are problems that through practice definitely get a lot faster. That's why I recommend problems from your textbook for extra practice. I want you to get a decision of, okay, how much do I need to do to get good at this? For some people, some of these are really quick. Some people, they need a few more practice problems. And that's up to you to figure out how many of these do I need to solve to get to where I'm really comfortable. When I see this, I can just go, and I don't have to stress and think about it too much. So with that, I hope this went well, and I will see you in a later video.